Hi, my name is Shadaj Laddad. I'm an undergraduate student at UC Berkeley in my third year. Today I'm going to be talking about fluid quotes, a new approach to metaprogramming that lets users manipulate quotes alongside runtime code while splicing at compile time by tracking the code through dependent types. This work was advised by Professor Koushik Sen. So, to get started, let's talk about why fluid quotes matter. Metaprogramming is a very powerful tool for both optimizing performance by inlining pieces of code which are related in complex ways, as well as enabling new types of APIs like language-integrated queries by offering more advanced analysis at compile time. But oftentimes, especially with functional programming, we run into the limitations of abstraction boundaries. For example, consider this code. We have a preprocessor in one module, in this case it's just a simple square function, and then we have our main function, in which we are trying to use preprocessor as part of a larger function that we want to take the derivative of. This differentiate function is backed by macros, which is one of the most common tools we have for metaprogramming. But we'll run into an issue here if we try to access the definition of preprocessor in our differentiate implementation. You'll notice that we can't do this safely since the processor is just an opaque function. We know its type, but we don't know its implementation. These types of abstractions get in the way of our analysis since now we can't differentiate the function. We also can't make structural changes to this program to use regular inlining without modifying the behavior of the code. Since preprocessor is loaded into a variable and any attempt to inline it would result in different behavior since getPreprocessor has a side effect. What we need to do is resolve the AST of preprocessor at the splice site. And we want it to flow with our function value since we cannot make structural changes either. We could try to modify the differentiate macro to trace back the reference to the preprocessor, but this quickly becomes brittle since the macro would have to handle all the different language features that may be involved when passing the function. But many modern languages actually have the capability to flow the AST data we need across abstraction boundaries. We can use dependent types. We can add dependent types to this function value which flow across the abstraction boundary through the regular type propagation implemented by the host language. And that's the basics of how fluid quotes work. When you wrap an expression using a fluid quote using the quote function, instead of returning the original function, you return a fluid function. The fluid function captures the expression, in this case just serializing it as a string. When we call splice call another fluid quote API, we can grab the captured code from the dependent type and splice it in at the call site, performing transformations to rewire the parameters as necessary. So when splice call is expanded, we see that we just have a simple square function that replaces it, and now have code that the macro can analyze. So now that we've seen the power of fluid quotes, let's talk about how it works. The base definition of fluid quote is quite simple. You just track the expression you want to capture with the dependent type. In our implementation, we use string literal types, which let us store the serialized AST as a string. Then you have two API methods. The first one, quote, takes the value of type t and wraps it into a fluid quote of type t by serializing the AST into a string. On the other hand, splice looks up the captured code at the call site from the dependent type and splices it in. In order to maintain correctness in more complex situations, we'll build on top of this definition to add support for features like closures. But this core is enough for an initial exploration. Note that under the hood, quote and splice are actually regular macros. They integrate with the type system so that when we call quote, the macro can generate a new type that captures the AST. But then the user can just pass the quoted value across abstraction boundaries, letting the host language's type system propagate the AST. Finally, the splice macro inspects the dependent type containing the captured code, deserializes the AST, and splices it in at the call site. When dealing with fluid functions, we have an additional splice call macro, which performs a transformation to rewire the function parameters to use the given arguments instead. Now, in simple situations, we can just grab the captured AST and dump it at the splice site. But this isn't safe, since there may be references to local variables that we need to handle carefully. In addition, we need to maintain hygiene by making sure that local symbols at the splice site don't indirectly affect the spliced code. So when quoting, we need to identify any local references and keep track of them with closures, just like regular functions. At the splice site, we can emit code that loads those references from the runtime closure object. So let's take a look at this example. In this example, we have a function where a is a local variable. And so if we were to just splice the fluid quote anywhere outside this method, we would run into a problem because we won't have access to a. To handle this, we identify a as a local reference and generate an element for it in a runtime closure object, and also introduce some additional dependent types, some metadata that tracks the references that are handled by closures. We also transform the AST before serializing it to replace all closure references with distinct names. However, using closures comes at a performance cost that we want to avoid, especially since fluid quotes can be used for performance optimizations. So when identifying references that need a closure, the quote macro performs extra checks to minimize the number of closure entries that are generated. We can skip generating a closure if we have a stable public path, which means that we have a path all the way from the root package to the symbol we are referencing that only uses public immutable values. In that case, we simply substitute the reference for the full path instead, which avoids a closure without affecting the program behavior. In addition to using fluid quotes to track ASTs for later analysis, fluid quotes also come with their own composition API that offers a lightweight approach to metaprogramming. Instead of having to write a full macro that involves additional language features, developers can use the quote and splice APIs to compose fluid quotes, even when the specific ASTs of some quoted inputs are unknown. In this example, we have a method that takes multiple quotes. When type checking the body of this method, dependent types of these inputs will be abstract types. So instead of splicing them, we just emit references to the input quote types. When the function is called, the abstract types will be resolved to concrete ones, so the composed quote can then be spliced at the top level. This also extends to more complex generative macro style metaprogramming, where we build templates out of quoted components. In this example, from the user's perspective, there are no advanced language features for metaprogramming involved. Fluid quotes can be used just like regular objects and can be composed as if the metaprogramming logic was being executed at runtime. But unlike systems like LMS, which only operate at runtime, the resulting quoted code can be spliced at compile time, since we track the ASTs through the type system. Finally, let's talk about the applications of fluid quotes. In our paper, we chose two specific applications to explore both performance and advanced analysis angles of fluid quotes. Our first application targets stream fusion, a critical component of functional APIs, since the overhead of applying multiple transformation functions one by one is quite high. For example, in this code, the overhead of the individual function calls introduces a large performance penalty, but if we rewire our code to just use a single function instead, it's 2.7 times faster. So there are a lot of performance gains to be unlocked by stream fusion. But current stream fusion approaches have the issue that we explored all the way at the beginning of the talk, that they don't handle abstraction boundaries. If you define a couple steps of your transformation in one function and a couple in another, you can't fuse all the steps together because the compiler will only be able to fuse functions in a local context. In our evaluation of fluid quotes, we created a library called Pipelines, which offers core stream APIs with fusion powered by fluid quotes. Pipelines have three key methods. You can map, which transforms every element of a pipeline according to a function, scan left, which accumulates some transforming value, and lastly zip, which allows us to merge together streams. With fluid quotes, pipelines can take code like this, where you have multiple steps, and fuse them together into a single imperative efficient function. But unlike existing stream fusion implementations, pipelines can also fuse transformation steps across abstraction boundaries, just like the challenging example we just saw. So let's go through the whole process in pipelines. You start by creating a pipeline. We have regular stream APIs, and in these API implementations, there's no metaprogramming involved at all. We just do regular type manipulations where each of these steps builds up a tree of types. We call this tree the structure of the transformation. We define types corresponding to each of these types of transformations, map, zip, and scan left, which internally keep track of fluid quotes. This allows us to track the individual functions to be fused together at the end. In addition to the structure type, we also keep around a runtime instance containing the closures associated with these fluid quotes. Next, when the user calls the instance method to generate a fused implementation of the stream, we enter macro code that will perform this final code generation. We take the structure type and convert it into a graph. In this case, we see that the graph is actually just a linked list, so we have a simple pipeline here. We traverse this graph and generate the code for every step of the transformation. At this point, we apply fluid quotes APIs to splice every transformation fluid function with the argument set to the results of the previous step. Once this graph traversal is done, we have a full AST of the fused pipeline that will be spliced into the user code at compile time. But there are more complicated situations as well. Consider this code, where we generate a base pipeline, transform it, and then zip it with itself. Many existing stream fusion implementations follow an execution model that would result in double calculations of the base. For example, languages like Rust would force you to clone the shared stream, which results in a double calculation. But with fluid quotes, we can use our global knowledge of the computation graph to offer stream fusion while also making sure that we are not doing unnecessary computations. At the type level, there's no information telling us if two nodes correspond to the same stream, but if a node and all of its dependencies are identical, we can insert a runtime check to only perform a calculation if the two nodes are different. By checking for subgraph equivalency at compile time, we minimize the number of such runtime checks, which results in better runtime semantics while still maintaining performance. So, with fluid quotes, pipelines solve the challenges of stream processing we saw earlier by propagating the computation graph through dependent types. Even if your transformations are defined across multiple functions, through the type system, the final fused pipeline is able to optimize based on the knowledge of the entire compute graph. As part of this evaluation, we developed a few benchmarks that show how fluid quotes combined with a stream fusion algorithm can result in great performance improvements. Our benchmarks represent a wide variety of challenges, going from just a few steps where the individual functions are quite complicated, to ones where we have a lot of lightweight functions. Across all these benchmarks, we see significant performance improvements. And since fluid quotes handle the types of abstractions that frequently show up in production code, this approach to stream fusion is much more amenable to use in real-world applications. Another application that we explored was language-integrated queries. Language-integrated queries make it possible for developers to query databases by writing code in a functional programming manner, using the regular transformations like map and filter. LINQ uses metaprogramming to analyze the functions passed to these transformations to generate the equivalent SQL statements. But as we have seen, traditional approaches to metaprogramming cannot handle abstractions, like the one in this example where we abstract over a predicate for filtering elements of a table. So if we use Quill, an implementation of LINQ for Scala, in this case it'll just fall back to generating queries at runtime since it cannot track the flow of this predicate function at compile time. But with the very lightweight layer on top of Quill that adds support for fluid quotes, we're able to solve this by instead passing around fluid quotes instead of the Quill quotes. With fluid quotes, the body of the predicate is tracked through dependent types and propagated by the type system. So at the end, when we want to generate a SQL query, we can do this at compile time, since the predicate can be resolved to an ASD by just inspecting its type. Fluid quotes enables a lot of advanced metaprogramming analyses like LINQ to operate at compile time, which results in a better user experience since problems can be caught earlier, and eliminates the types of runtime overhead seen with systems like lightweight modular staging. So that's fluid quotes. Fluid quotes makes it possible to bring quotes side by side with runtime code, while still being able to splice them at compile time. With fluid quotes, metaprogramming applications like Stream Fusion and LINQ can be made more flexible to abstractions, since fluid quotes can pass across abstraction boundaries without any trouble. Our implementation of fluid quotes is open source and you can check it out on GitHub. And now I would like to answer any questions. Thank you.